All right, today I'm talking about Euler's method. Euler's method is a tool that was going to help us with differential equations. It's one a very small aspect of his collective body of works. So just wanted to take a second to recognize this. This is Leonhard Euler. He was a Swiss mathematician. He lived approximately the same time as Ben Franklin across the Atlantic Ocean. But whereas he's maybe not one of the most well-known names in mathematics, I don't have a good reason for why he's not. He he has one of the maybe the biggest output of any mathematician out there. What I was hearing this morning when I was preparing for this video was like, and this came from a video in the late 90s, that in 1910 they started this project that was attempting to publish his collective body of work, and so they produced one volume in 1910. It was like this big fat book, like bigger than the textbook that you use for this class, and it was just the first volume. And at the time the video that I was watching was produced, they said there were over 75 volumes, and there was really no end in sight to producing the collective works. He produced an enormous amount, and he did a lot of it while he was disabled. In 1730, he lost vision in one eye. In 1771, he went blind, and he actually increased his production when he went blind, which I think is really the amazing part. That's part of why I'm giving him this testimony now, because he not only overcame his disability, he found a way to turn it into his advantage. He had an amazing memory. He was able to commit logarithms to his memory, which at the time, logarithms, they had these tables that people read logarithms out of, like with 9 decimal places, and he was able to just commit those to memory. And so his enormous memory served him well when he went blind, because he was able to cite things, and he had a team of scribes working with him, writing down everything that came out of his mouth, and he had scribes that would read to him the papers that existed at the time. And I think it's really just this amazing story of a mathematician who's has over 96 things named after him, which is quite a lot. And today we're going to talk about one very small part of those, which is Euler's method. Euler's method has to do with differential equations, and it specifically has to do with differential equations that are inseparable. A differential equation is inseparable if it's separated by addition or subtraction. If you think of what happens when I have dy dx is equal to y squared x, I can separate these things. So I get 1 over y squared dy is equal to x dx. And then once I've separated these things and they're being multiplied, I can integrate both sides. That's a legal maneuver. That works, okay? Euler's method is something that we can do when we're encountered with situations where that's impossible. And so if you think of what's going to happen when I try to separate, I'm going to get negative y squared plus dy dx is equal to negative x. And if I try multiplying everything by dx, I'm going to get negative y squared dx is equal to dy, or my bad, plus dy is equal to negative x dx. And there's just no way, like, even if I could move that dx over there to the other side, I'd still have a plus in here. And so this whole like integrating both sides would be illegal. It would be totally illegal. And it wouldn't provide the estimate that I want. So what I'm going to do with Euler's method is we're not going to get exact answers, but we're going to fish around and see what we get. So the way to think of it is like, I'm going to kind of like start somewhere, and I'm going to take a step in a certain direction. And after I take that step, I'm going to reevaluate it. I'm going to take another step. Okay. And I'm going to keep going until I've gotten to wherever it is that I'm trying to get to. And if I want to be more accurate, guess what I can do? I can take smaller steps, okay? And if I take smaller steps, I'm going to get to a little bit different places. And notice that you can take steps that are super small, and it'll be more accurate. And you can probably already make the connection that with technology these days, you can take steps that are almost infinitely small. But another thing is just, this is a good lesson to remember about slope fields, is that what matters is where I start. Okay, so if I start wherever I start, affects where I'm going to end up. So it's not like there's just one specific path. It's very sensitive to your starting point. It's a little bit like, I think, the currents in the ocean. It'd be like if you picture this as an ocean and we don't actually know which way the currents are flowing. A slope field is like, with Euler's method, is like dropping down a bunch of lifeboats or the little rafts and just kind of watching what direction they flow and then using all those flows to map the directions of the currents. But in our case, what we're going to do is we're going to use it to approximate one specific point. So let's say I dropped that little lifeboat at the point 0, 1, and I want to know where it's going to be at when x is equal to 2, or I want an estimate of it. So I'm going to specify the number of steps. And in this example, the technical part is actually going to be really easy. I'm using 2 steps, which means delta x is going to equal 1, right? Because I'm trying to go from 0 to 2, and I'm taking 2 steps, so each step is going to be 1. And to me, the way this makes sense is through a table. I've always thought Euler's method makes best sense through a table. So I start at 0, 1. I'm going to evaluate dy dx. When I put 0 in for x, I get 0. 1 in for y, I get 1. And then I'm going to move 1 on the x value because that's my step size. And then I have to figure out how far I'm going to move on the y side, which is going to be 1 also, because that's what dy dx is. Notice, because this confuses people when I start with an obvious first example where step size is equal to 1. But if step size was equal to 1/2 there, dy would also be 1/2. Okay, so you're multiplying those two things together. And then in your next point, I went up 1 on the x value. So 0 plus 1 is 1. I went up 1 on the y value. So 1 plus 1 is 2. Then I'm going to put these numbers in again for y squared minus x. 2 squared minus 1 is 3. Okay, so my dx is going to be 1 again, and my dy is now going to be 3. So what's my new point? I'm going to go up 1 on the x, that gives me 2. I'm going to go up 3 on the y, that gives me 5. So my estimate for f of 2 is not exactly, because it's an estimate, but approximately 5. That's how Euler's method works. To me, the table really helps me, because when you get going and you're taking the AP test, or the next time you get asked this is going to be in the middle of a chapter when you're learning something else and you're going to forget all that there is to know about Euler's method. But for me, the way that I remember it is with this table, because from that table, I can kind of work backwards. And knowing the fact that it's a simple linear approximation, so that I don't have to spend I don't have the memory like Euler, where I can just send everything up there and expect to retrieve it at any point. But working backwards from this table is how I do it in my own head.